Okay, so as you see over there on the left, I simplified our hermeticity condition, having gone through all that then. So what we're going to need then is, because when you do an integration by parts, those two terms will be equal from the standpoint of, okay, flip the sign and move the derivative to the other term. But there's a boundary term, and the boundary term then is going to have to evaluate to 0. So if for all the f of x and g of x in our space of functions, the boundary term always vanishes, then we'll have what we need for our operator k representing minus I dx to be a Hermitian operator. So we have to look at that a little bit. So when will it be true that we get away with this? Well, there are certainly some functions of interest in quantum mechanics where we get away with this. So for example, if you're in the infinite square well, then you're dealing with a situation where the wave function always has to vanish on the ends of the infinite square well, right? So infinite square well from x equals a to x equals b. Boundary condition says psi of a equals 0, psi of b equals 0 for the infinite square well. So we can put a big check mark there, because any functions that are allowed for our infinite square well vanish on the boundary, and so therefore, you know, what this really evaluates to is g star of b f of b minus g star of a f of a. Well, that's certainly 0 for functions which vanish at a and at b. Certainly the boundary term vanishes. So in that class of functions, k is Hermitian. Woo, yay! There's much rejoicing and all that sort of thing. If we have normalizable wave functions for minus infinity to infinity, let a be minus infinity and b be infinity, then we know that psi of x goes where as x goes to as x goes to plus or minus infinity. What happens to psi off in the distance for normalizable wave functions? It goes to 0. Otherwise, you couldn't normalize it. So that gets a check mark too. Look less than happy. Okay. Happy? Okay. Happy? Joyful? Yeah. Did you go joyful? Okay. So that would be fine. But uh-oh. What about if we let the psi k of x into our space, into our party? In other words, what if we let those eigenfunctions of the k operator, 1 over root 2 pi e to the ikx, in our party? So if I take, say, f of x is equal to psi k of x, g of x is equal to, let's say psi k prime of x, then g star of x f of x is equal to 1 over 2 pi, and then we're going to get e to the ikx and e to the minus ik prime x when we do the g star business. So e to the I k minus k prime x is what g star of x, f of x is, if I did that right. I believe I did. Because f of x is 1 over root 2 pi e to the I kx. G of x is 1 over root 2 pi e to the I k prime x. So when I star g of x, I get e to the minus I k prime x. What does this do as x goes to infinity? Does it approach a limit as x goes to infinity? It doesn't, right? Because this is 1 over 2 pi cosine k minus k prime x plus I sine k minus k prime x. Cosine and sine just wiggle, 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 wiggle. And in fact, I could say plus or minus infinity. It wiggles on either end. This just wiggles. It just wiggles. So what's going to happen to our boundary term? It doesn't do anything in particular. So what do you suggest we do? Would we like k to be Hermitian? We sure would, because when I multiply it by h bar, it's the momentum operator. And Hermitian operators do good things. They're guaranteed to have real eigenvalues, and their eigenfunctions form complete sets. And we would like this to be true for our k operator, because we want it to be true for the momentum operator. So what should we do? Well, you think like a physicist, and you say, I'm just cheap. I'll just doctor it up. So let's cheat. Doctor it up. What we'll do is we will define the limit like this, that the limit as x goes to infinity of e to the I kx e to the minus I k prime x is going to be the limit as L goes to infinity and as delta goes to infinity of 1 over delta times the integral from L to L goes to minus infinity, I should say. As L goes to a minus infinity and delta goes to infinity of the integral of 1 over delta, integral from L to the L plus delta of e to the I k minus k prime x dx. So, in other words, as those guys go to infinity and minus infinity, the integral is going to go to minus infinity to infinity here, but we're dividing by the length of the interval. In other words, we're defining this to be the average value of e to the I k minus k prime x over the interval in question. We're defining, no, I'm sorry, I really do mean plus, I goofed there, I really do mean plus infinity there for L going to plus infinity as well. Because, I'm sorry, I got myself confused. In other words, what we're going to do is we're going to go way out to large values of positive x, out to some other really even bigger large values of positive x. And so in the limit that these both go to infinity, I'm looking at this interval that's getting longer and longer and longer, and also heading out to infinitely far away. So I'm sort of thinking of myself as, okay, I want the limit of this thing as x goes to infinity. What I'll do is I'll define it as the average value of the function way over there, right, at infinity, so to speak. So I'm thinking of that as the average value of e to the I k minus k prime x at x equals infinity. And then there I am with my eyes averted, because I'm not looking a mathematician in the face as I say this. So there's some mathematician who knows who it might be, and I'm not able to look at that mathematician, okay, as I say this. And well, the nice thing is that that's going to be 0 because this just wiggle, 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 and if I average over some interval, it goes to 0 because it just does, right? Because this is just wiggling, and so, and it turns out this is okay. Turns out this works. It's okay. And so we can therefore we get to declare K to be Hermitian on these grounds. It turns out it's okay. And the idea here is we generalize the idea of normalizable wave functions to say it's also okay to include wave functions which aren't strictly speaking normalizable, but they can still be normalized to the Dirac delta function. That's essentially what we've said, is that we can allow our space to contain wave functions which are normalized to the Dirac delta function. The integral of one star, the other is delta of k minus k prime for these guys. So we're including wave functions which are strictly speaking normalizable. You can actually make them have area under the curve of 1. And wave functions which aren't strictly speaking normalizable. But on the other hand, well, they sort of are, because the area under a Dirac delta function is 1. And so it turns out it's okay to do that, and I'm not going to say any more about it. Trust me, it's fine.
How is it visually possible?
Oh, be quiet. Trust me, it's fine. All right, we're just going to keep moving. Pay no attention to the man behind the curtain. So now that I've got you to fully and cheerfully buy into that, suckers. No, actually, you're not suckers. It's okay. It's okay in the same way that the Dirac delta function is okay, right? You swallowed that, didn't you? Swallow that too. More pills to swallow there, okay? So now here's where we get something. Every time I see that, it's just like, oh, this is just too cool, right here. Okay. So here we go. Since K is Hermitian, K is Hermitian, it's orthonormal eigenfunction sense that their integrals against one another are 0 if the k's are the same, infinity if they're not, such that the inner product is a Dirac delta function. K inner product with k prime is delta of k minus k prime. That's what I mean by orthonormal in this sense. Form a complete basis, which is really an oxymoron. There's no such thing as an incomplete basis. By definition, if it's a basis, it's complete. Form a complete basis. In other words, we can expand any f in terms of them. We can expand any abstract ket f on the capital K basis. Given the projection of f onto x, which is what we call f of x, how can we find f projected onto k, which we'll call f of k? How can we find the representation of our abstract f in the k basis? Now, I don't know if you'll have this reaction, but the first time I saw this, it made my day. So I don't know if you'll feel the same way, but this is one of my favorite things ever, is the following. Okay, so f of k is equal to inner product of f with k, the projection of f onto basis k, vector k in the k basis, I'm going to insert the identity in terms of an integral over outer products of x. So in other words, I do that. I put in the identity in the form of integral over outer products of x in between k and f. But f projected onto x is f of x, and x projected onto k, well, we already know what k projected onto x was, right? We said that's 1 over root 2 pi e to the ikx. So x projected onto k is 1 over root 2 pi e to the minus ikx. So this becomes that integral, minus infinity to infinity, of 1 over root 2 pi e to the minus ikx f of x dx. What does that integral represent? The Fourier transform of f of x. Holy crap, basically. So in other words, the representation of f on the k basis is the Fourier transform of the representation of x, of f on the x basis. They have a Fourier transform relationship to one another. So going from the function to its Fourier transform is simply expressing the same vector in two different bases. F of x is f expanded in terms of the x basis. Its Fourier transform f of k is the same thing expanded in terms of the k basis instead of in terms of the x basis. So it's as though what we're doing is just changing bases, in other words, and expressing the same thing with respect to two different bases. We're just expressing the same abstract vector in terms of two different bases. And then remember we talked about the idea of a generalized Fourier series. We said that for the eigenfunctions of any Hermitian operator forms a complete set. For example, we had the Hamiltonian as a Hermitian operator. We said that the eigenfunctions of the Hamiltonian form a complete set. Any function can be expanded in terms of them. So we have this expression, we can say we can have this complete set of functions such that f of x is a sum of the Cn psi n of x. For example, the psi n of x could be the eigenfunctions of the Hamiltonian. For the infinite square well, for the harmonic oscillator, whatever. For the infinite square well, it is a Fourier series because the eigenfunctions are sines and cosines. For the harmonic oscillator, they're Hermite polynomials times Gaussian things, so it's more complicated, but it's still the same kind of expansion we do. And we always said this, let's use Fourier's trick. You multiply both sides by psi m star, integrate over dx, and use orthogonality. Let's look at that from a different standpoint. Let's say that f is the sum of the Cn psi n as abstract vectors living in our space. And here, we haven't said whether we're using the x basis, the k basis, some other basis. So we've left it unspecified. We've just got this function living in this abstract infinite dimensional space. What basis will we use to express its components? I don't know. Let's leave it unspecified for now. Take the inner product with psi m. Product with psi n says f projected back onto psi m is sum of the Cn inner product of psi m with psi n. But the basis of our Hermitian operator which generated these beasts can be made to be an orthonormal basis. So the inner product of psi m with psi n should be the ordinary Kronecker delta, delta mn, because the different eigenfunctions are orthonormal to one another. So this inner product ought to be the Kronecker delta function. So what does the sum collapse to? C sub m, single term C sub m. So generically, in an expansion like this, C sub m is the inner product of your abstract vector f with basis ket psi sub m, written as a bra. Yes?
So why not the Dirac delta?
Because these are a discrete set of functions. So we're summing over integers here.
So if we have so if we do it the integral way, then that will become the
Right. See, the thing is, the eigenfunctions of the k operator right? Psi k of x equals 1 over root 2 pi e to the I kx. K can be anything, any real number. So that is a continuous index. If you have a continuous index, that's when you have to use the identity in the form of an integral when you do one of these insertions. But here, this is a discrete index. It's not a continuous index. It only takes on integer values, or can be made to only take on integer values. In other words, we're talking about the case where the eigenfunctions there's an infinite number of them, but it's a countable infinity. They can be mapped onto the integers so that you can sum over a discrete index as opposed to integrating over a continuous index like we had to do over there. So this is the abstract expression for what C sub m is. In the x basis, and I'm going to write it as a capital X because I want to think it's an abstract x operator. What I can do is I can insert the identity. So I do psi m x x f dx. X is a continuous variable. It can be anything. So the identity in terms of x looks like this. In terms of the psi sub m's, the identity looks like this. Sum over n of these outer products. It's a discrete summation because there's a countable basis. There's an infinite but countable number of basis vectors. The wave functions, that, if we're talking about quantum mechanics, are like those of the infinite square one, right? They're labeled with an index n, which is an integer. There's psi 0, psi 1, psi 2, psi 3, psi million, and 6. You can map the eigenfunctions onto the integers. So in that case, the identity becomes a discrete summation. But with something like x, x can be anything, so the identity becomes an integral over outer products instead of a sum over outer products. Now, what is this? This is f of x. What is this? That's psi m star of x. dx, that's the formula we developed before with Fourier's trick of multiply by psi m star, integrate over all x, and use orthogonality. I get exactly this formula out of it, but in the Dirac notation, glory be and hallelujah, you just do this. You use, oh, they're orthogonal to one another. Now I'll insert the identity and turn it into something that I can use in a particular representation. But note, I could also be using the Fourier transform functions. In other words, it's also true that Cm is given by this integral. It's the integral of the Fourier transform of f multiplied by the complex conjugate of the Fourier transform of psi sub m. It's the exact same formula. So the neat thing here is this works in any basis whatsoever. We've looked at two particular, the x and k basis. This is a general formula. It doesn't have to be done in the x basis. It works in any basis because I can insert any basis identity in there. So again, it's like, holy crap, you know. This is where you start to really see the power of the Dirac notation and how it unifies things which before didn't seem so obvious to unify with one another. And Fourier's trick is this lengthy thing that is kind of easy to forget what it is. Here, it looks like we're just taking dot products of vectors with one another and then inserting other bases dot products in and outer products in order to change them. So it turns Fourier transforms and Fourier series into just generalizations of the ideas of taking dot products of vectors with one another and expanding vectors in one basis or another basis and so forth. Yes?
So for those two lines, if we go from fk to fx, we have that. So how about psi m stars k to psi m stars
right, so this is the Fourier this is the complex conjugate of the Fourier transform of psi m of x, because psi m projected onto k would be k, x, x, psi m dx, right? This is 1 over root 2 pi e to the minus I kx, psi m of x dx. So this is the Fourier transform of psi m of x. Since it's appearing conjugated here, it's the complex conjugate of the Fourier transform of psi m of x, which is psi m of k, which is psi m star of k. So it doesn't matter what basis you use. And if we're going between x and k, everything's just replace things with their Fourier transforms, and you're good to go, essentially. So Fourier transform both these suckers, and you get an equally valid relation for C sub m. Now, if you knew these already, you'd be stupid to Fourier transform before taking this integral, right? But what if you were working in the k basis to begin with, you know, or whatever? And then also it's just theoretically interesting that actually this expression is perfectly general. You don't have to be working with functions of x. You can be working with functions of k, where then you're working in Fourier transform space instead of in x space, if you will. So there's this beautiful unity. I mean, it more than made my day when I understood this. I mean, made my month when I understood this first. I was sitting like, I understand something I didn't understand before much better than I did before, and all that stuff. I didn't actually go around like, I understand something that people feel like, but people might do that anyway. But anyway, all right. Happiness and joy. Boundless happiness, infinite joy in our infinite dimensional space. Here's something else. In the k basis, the effect of the k operator is to multiply f of k by k. And I can see that as follows. What if I apply k to f and project back onto eigenvector with eigenvalue little k? Now let's insert the identity not in terms of x, but in terms of k's. So in other words, I'm going to insert outer products k prime and integrate over k prime. Yeah, I know, so gotta be careful here. That's a capital K, and everybody else is cute little k's. Now, by definition, capital K applied to this eigenket little k prime, labeled with little k prime, is little k prime times that eigenket. So out comes a cute little k prime. And then inner product of k with k prime. F of k prime, f on k prime dk prime. What is the inner product of f with k prime? Yeah, it's what we'll call f of k prime. F of k prime. If we knew f of x, that's its Fourier transform evaluated in k prime. What is this beast right here? What are the inner products of the k's with each other? Delta of k minus k prime. dk prime. Oh look, I have a delta function integrated against something, which means the effect is substitute k prime equals k everywhere you see a k prime in the integrand, because we're integrating over k prime here. So therefore, k prime clicks at a value of k everywhere you see the things that you multiply the delta function by. So this is k f of k.
But I wonder, we just pull the k prime out first?
We can't because this is an integral over k prime.
Oh, yeah.
So it's not a constant.
Right.
Right. If it were an integral over k, we could do that, but it's not. So you have to be careful with distinguishing what's held fixed and what's being integrated. K here is being held fixed. K prime is being integrated here. So, in other words, we conclude that what k does to functions, if you express them in terms of k, is simply multiply them by little k. So in other words, he said, trying to find the appropriate piece of paper, yes, somewhere. So in other words, we have the following table, that the k operator applied to some function of k is equal to just multiplication by k. The k operator applied to some function of k just means multiply that function by the variable k in the k basis. Multiplication, so application of k means multiplication by k. In other words, apply k to the Fourier transform of a function and just multiply by k times the Fourier transform, if you like. Whereas, we already know that k applied to some function of x means to find minus I df dx. That's in the x basis. Or in other words, as operators, capital K is simply represented by multiplication by k in the k basis, but k is represented by minus I ddx in the x basis. Put in kind of more standard terminology, you can put it in terms of Fourier transforms. In other words, the Fourier transform of minus I times the derivative of a function is k times the Fourier transform of the function. That's an identity from Fourier analysis, is that the Fourier transform of minus I times the derivative of the function with respect to x is simply k times the Fourier transform of the function f of x. And that's what this means in operator speak. Okay, any questions about that?
So f
Yes?
is not eigenfunction of k, only f.
No, this is an arbitrary f of x. It's not an eigenfunction of anybody. It's just an arbitrary f of x. It's just an arbitrary f of x. So in terms of Fourier transform theory, what this is saying is that the Fourier transform of minus I df dx is k times the Fourier transform of f of x. Because f of k is the Fourier transform of f of x. So this is saying minus I, the Fourier transform, like if in a math class one might see Fourier transform of minus I df dx is equal to k times the Fourier transform of f of x, is how that would be written in short Fourier transform theory. And we're saying as operators, that shows up here, because this is telling us the rules, how we can view it as when we're applying it to functions, basically. Because k and x are variables which are Fourier inverses of one another, so to speak. They're not inverses, but they're a Fourier transform pair. One shows up in the Fourier transform, one shows up in the function. Although it doesn't matter which one you start with and call the function and which one you call the Fourier transform. But that's the idea there. Any other questions?
What's that, the fancy F?
Oh, this fancy F means Fourier transform of the beast inside of it. Yeah, sorry, that's Fourier transform of the beast inside of it.
Is that a good letter?
It's a capital script F written very poorly because I never write script letters anymore, except when I sign my name. I always print. So my script writing has gone to hell, except for when I sign my name. Because that's often used for Fourier transform, script curly F like that. It says Fourier transform of minus I df dx is k times the Fourier transform of f dx. The effect of the operator x, whose eigenkets are the x like that. So we're labeling the ket with the eigenvalue little x. Or in other words, those are the beasts that have the property that x operator applied to them is eigenvalue times them. Is complementary to that of k. And by that I mean big K, the operator. So they complement one another. Oh, X, you're looking beautiful today. Oh, you have never looked better than you do in that top, and so forth.
Is there complex conjugates about that?
Not quite, actually. They're simple. They're simple. No. So let's show what I'm getting at here. So let's do this. Let's project x applied to f onto x. So it becomes a mantra. Insert the identity written as an outer product. So I'll integrate over outer products of kets and bras x prime, inserted in between the capital X and the F. And then we'll say that this beast right here is going to be equal to x prime delta of x minus x prime, right? Because the inner product of x with x prime is delta of x minus x prime. And x applied to ket labeled with x prime is x prime set times set ket. Does that make sense? I can throw it in one more line if I need to, right? Because this is x prime inner product of x with x prime, which is x prime delta of x minus x prime. Meanwhile, f projected onto x prime is f of x prime. And what does that integral simplify to? X, f of x. So just like in with respect to functions written as functions of k, the action of capital K is just to multiply by the variable little k. The action in the x basis, we say, of x on functions f of x is to just multiply those functions by x. In other words, that's what we've said all along, that what the x operator does is multiplies functions by x. But what about if we're not in the x basis anymore? What if we're in the k basis? What does f do? I wonder. Let's find out, shall we? wires or something. Yeah, like Wayne's World. You guys know Wayne's World? Yeah, okay. Not that I did the accent well, but in any case, let's do this beast. Let's apply the x operator to f and project onto k. Now I'm going to insert the identity twice. I'm going to insert it once in terms of x and once in terms of k prime. Like that. So I've inserted the identity twice between x and f. And you'll see why in a moment. Basically, it's because I want to be able to have everything be the appropriate functions of what I want it to be, essentially. Yeah, that's clear. So, the x operator applied to ket labeled by little x is x times that ket. So this becomes x inner product of k with x. In the middle, I've still got inner product of x and k prime with one another, and still k prime inner product with f, dx dk prime. And then I have to start translating these into functions. So the inner product of x with k is psi k star of x, right? Because k inner product with x was psi k of x, the eigenfunction of the operator k with eigenvalue little k. So this is going to be 1 over root 2 pi e to the minus I k x. That's what that beast becomes. And I'm banking, apparently, O time for you guys. By the end of the semester, I'm going to owe you an hour, apparently. But I'm sure you'll have forgotten by then, right?
Actually not. We'll keep track of it.
Your zest for learning will have grown so large by then that you'll not want it back anymore. This is 1 over root 2 pi e to the I k prime x. Because here I've got eigenfunction psi k prime projected back onto x. That's 1 over root 2 pi e to the I k prime x. And the last piece there is f of k prime. Dx dk prime. So now I do some rearrangement. I group the 1 over root 2 pi's together. I group the exponentials together and write e to the I k prime minus kx. I can rearrange integrals in a multiple integral, so I'm free to make that an integral on x, and then later do the integral on k prime. And meanwhile, multiplication by x inside the integral is the same thing as taking the derivative with respect to k of this integral right here times I. Because notice that this integral is equal to 1 over 2 pi derivative with respect to k of e to the I of e to the I k prime minus k x dx. What's the derivative with respect to k of e to the I k prime minus kx?
We have we have I k negative kx.
Yeah, minus I k times e to the I k prime minus kx, right? If I take the derivative with respect to k of this, I get minus I k times e to the I k prime minus kx, which when I multiply by I gives gives, no, I'm sorry.
Gives k, yes.
No, it's actually, it's minus ix. I'm taking the derivative with respect to k. So it's minus ix, not minus ik, minus ix times this.
So you get
Then I multiply by I, and I just get x.
That's so deep.
But it's true, isn't it?
Yeah,
Right?
it's
It's
true.
true. It's true, it's true, it's true. Right? So this beast right there, that derivative then becomes, this is 1 over 2 pi times ix e to the I k prime minus k x dx. So then when I multiply by I there, I'm going to, minus I, damn it, minus I x times all that. Then when I multiply by I, it'll turn back into x again. So the nice thing, though, is then that what this has turned into then is that this makes this I ddk of the integral of, well, what is this integral right here? 1 over 2 pi integral e to the I k prime minus kx dx. What is that integral? Delta of k prime minus k, or delta of k minus k prime. So this is I ddk of the integral delta of k minus k prime, or k prime minus k, delta is an even function, f of k prime dk prime, and what's the integral of delta of k minus k prime f of k prime dk prime? F of k. So this is I ddk f of k. So in other words, x applied to f of k is I ddk f of k. And that means that x is represented by multiplication by x in the x basis, like we've said all along, but x is represented by I ddk in the k basis. Contrast that with k, which is multiplication by k in its own basis, and is the application of minus I ddx in the x basis. So x and k have complementary properties. In the k basis, x acts like a derivative operator. In the x basis, k acts like a derivative operator. In the k basis, x acts like a derivative operator. In the k basis, x. But in the x basis, k acts like a derivative operator. So they're complementary to one another. And this can be turned into statements about inverse Fourier transforms. In other words, the inverse Fourier transform of I times the derivative of the Fourier transform with respect to k is x times the whatever I'm trying to say. It's time to go. So, in any case, you can translate this into more Fourier speak, in terms of what you might have seen before. Okay, so we're done, and I owe you another 7 minutes apparently. So keep on banking those minutes.